Welcome to installment 21 of writing a 6502 assembler in assembly language. And at the end of the last installment, I said I would go back to the scanner and make sure that we can find and return correctly the tokens, a forward reference to a temporary label and a backward reference to a temporary label. And so now is the time to do that. The scanner, that part of the scanner is in AS0, I believe. So go in there. And what we're looking for is get num, I think. Not found. So instead, let's look for tnum. There it is. Okay, get hex. Oh, it's called get dec. That's what we care about. All right, so here, the end of decimal literal, we check and see if the character was a colon. If it is a colon, let's say if it's not a colon, we unget C and return it as a tnum. If it is a colon, we go to get dec 8. So actually what we want to do, however, though, is not unget C yet. Instead, we want to see if after the number is an F. All right. And if it is, we'll go somewhere, which I'll just call 9A for the moment, or question mark. I just don't know where it's going to go yet. And we'll also compare to a B, which will mean a backwards reference. And that will go somewhere also. And if it's neither F nor B, then we're really going to unget the character and return it as a number. Now, if you remember, when we have this colon here, this is a temporary label or a numeric label. We also have to check and make sure that the value of this label is less than 10, because they can only be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And if there are, if that all works out, we'll jump to numlab, right, which is somewhere. But we also need to make this same check if it's a forward or backward reference like this. So it might be nice if we could just go to the same place here. But if we do that, we have to be careful. We maybe want to remember whether it's a colon, an F, or a B. Yeah, I think so. Basically, the situation is either I have to repeat this comparison code, or I have to repeat this code to check the value of the number to see if it's less than 10. And I think what I will do, I'll call this 9A. Oh, I have actually plenty of 0. Just call it 2. Yeah, actually, no, I have to repeat code one way or the other, but which one do I want to repeat? So let get decade. What if I just push this thing? Okay, get rid of that. All right, now I've checked to make sure it's a good numeric label. I get this back and I compare it to colon. Okay, if it's not a colon, go there. I'll just jump numlab, compare it to. All right, otherwise, the only way I get here is a numeric reference. In other words, if it's a colon, I go to it's something like this. Otherwise, here it's either something like this or something like this. One of these two things. And so I guess I'll just go through and check for each one in turn. Now, what if they want to use a capital F, capital B? Am I going to allow that? Typically, I allow labels to be, no, I don't allow labels to be, labels are case sensitive. It's the pseudo ops and the instructions which are case insensitive. So no, it must be lowercase. Get deck 3. Get deck 2. Otherwise, jump 4 lab. Get deck 3. It has to be a backward lab. I mean, it can't possibly be anything else. Otherwise, it wouldn't come here. So what I've chosen to do is just go to the label get deck 8 if my number is followed by a colon or an F or a B. All right, and if it's followed by a colon, F, or a B, it's assumed to be either a numeric label itself or a reference to numeric label, a reference to a numeric label, these two here. If it's not followed by a colon, not followed by an F, not followed by a B, it's just a plain old number. All right, so get deck 8 checks to make sure that the number's in the correct range, that is from 0 to 9. If it's not, it goes down here to give an error, but I push this on the stack, so I have to get it off. So just take it off the stack. All right, we don't care what it is. We're just taking off the stack and throwing it away. Okay, otherwise that it is between 0 and 9, and we just check and see, okay, we already know it's a colon, F, or a B. If it's a colon, go to numlab. If it's an F, go to forward lab. Otherwise, it's a B, go to backward lab. Okay. All right, so numlab is in a different file. That's all fine. And backward lab and forward lab can be in a different file. So we'll save that. Here's numlab. All right, and remember what this does is it creates this offset into, it stores the value of this label or it basically, there's like a linked list of the values of numeric labels, and it basically allocates the new space in the linked list. Hang on, let me just get the diagram I drew for it. Okay, here it is. So what the subroutine numlab does is basically put the label in the next space in this linked list. And remember, the linked list is made up of a block of 32 bytes. The first 30 bytes are 15 separate values for 15 successive numerical labels. Like if this is from numerical label 4, so 4 colon, another 4 colon, another 4 colon, another 4 colon, and so on. And we also, this B and F, though this is the important thing for the forward and backward references. So this is numeric labels here. All right, and here are those variables we need. So for lab, what we're going to do is get the Tocqueville. All right, and we have the forward pointer, the forward offset. Okay, so I guess we need to multiply it by 2, put it into X. We need to get the pointer. And that's going to be NLF pointer, numeric label forward pointer, X, right? And store that in our 0-page pointer, NLF pointer plus 1, X, store that here. All right, of course, that means we're going to have to preserve those things. Okay, and actually we can load Y Tocqueville. This is the offset into this pointer here is a pointer to one of these blocks. And then we're going to get Tocqueville, which is again 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, into Y. No, that's not right. It needs to be X. This is just the same thing we just got here, but we want it not multiplied by 2. And then we get NLF off, the offset, X. And this actually goes like this, okay? And then we move that into the Y register, because what we have just done is we have gotten this pointer here to the front of the block, and then we've gotten the offset into the block. And we'll use those things now to get the actual value of this the forward numeric label, and we'll store that in Tocqueville. Increment Y. So we've just copied. When we see, for example, 4F, we follow this pointer, which is actually a pointer and offset, to find whatever the current value of 4F is and copy this into Tocqueville. All right, and we're done. And now we're just going to basically reproduce all of this code. So let's use the copy and paste method here. No, don't delete them. All right, and this is going to be now backward label. And basically everything is exactly the same. Oh, actually, I did forget an important thing, which is I need to restore the 0 page locations. So we push low, push high, push low, pull high. Do it down here too. Okay, basically everything is exactly the same except for that we're not using the front pointer, we're using the back pointer. Back, back. There we go. All done. So with the FWD lab subroutine, we're just taking this right here, right? And with the BWD, we're taking this right here and finding whatever it points to and putting the value into Tocqueville. All right, and that looks nice. Okay, so we'll save that. All right, so now in our statement routine, when it here says, oh, I got a forward reference to a numeric label, it'll just unget that. Oh, did we? Let me just go check real quick whether I forgot something here. Okay, it's going to jump forward lab or jump backward lab. Yeah, it did forget something. I forgot to load the token type. And then down here also. That is T forward, T backward? I think so. Where is it? Yeah. Okay. T forward, T backward. So when it gets T forward, the value of that label is already in Tocqueville. So it will then go here, unscan it, and jump to expression. And one last little thing that needs to be done is to look for, and now I need to add these two, TFWD, 8C, T backward, 8D. Okay, we have expr type, expr val. So what we're missing at the moment is the routine expr. And we'll put that here. But for the moment, it's just return. All right, I made a lot of changes without trying to assemble anything, so let's assemble and find all of the ugly errors that are going to pop up. Well, 3 errors. Oh, okay, just missing operand ASL, and unidentified operation JSR expr. Okay. Names. Yep. Okay, that's probably, oh, that's down there in the, where I just added that stuff. Here it is. ASLA. Again, I don't understand why the assembler can't just figure it out. Why not just ASL? It could be ASLA automatically, but oh well. All right, and then okay, expr, JSR expr, JSR expr, expr. Oh, okay, that was dumb of me. Here, expr, and just return. Okay, still have some errors. Unresolved reference UNX error, label error. Oh, I never changed this. That's part of it. UNX. All right, and where is the error subroutine? Jump error, error. I see, but error is not an entry point, which is bad. It needs to be an entry point. All right. Okay, so no assembly errors, right? Are there bugs, errors in coding? Almost certainly, but no assembly errors. All right, so now it makes sense to go back and work on this expression parser. I think that it would be smart for me to show you an expression grammar so that you can understand how the expression parser is going to work. It's actually very simple. The expression parser, I'm just going to use the method of recursive descent, which does rely on the stack not getting blown out. So it does have on the 6502, because the 6502 has a stack of only 256 bytes, it has the disadvantage that a very large and complicated expression could blow out the stack and cause all sorts of trouble. But on the other hand, it's very easy to do. And it is unlikely that the stack is going to be blown out in any case, because the number of recursive calls is very likely not to be more than 10 or 12, which is 20 or 24 bytes of stack, and I don't think we will exceed that. And I don't think we will need to preserve any other kind of variables, although that remains to be seen. I've actually done a recursive descent parser in 6502 before, although it was a long time ago, and I recall it working, so it should work. So let me show you a grammar for the recursive descent parser. Okay, so here's the grammar. This, what this says is an expression is an OR expression. An OR expression is an AND expression with an OR operator followed by another AND expression. Well, it could be just an AND expression by itself. These parentheses means that this part here is optional. And there's basically an AND expression optionally followed by an OR expression and another AND expression, and as many of those as you want. So you could have something or something or something or something. An OR expression is either a bitwise or a bitwise exclusive OR. All right, and an AND expression is a sum expression with a bitwise AND operator and another sum expression. Again, of course, this part doesn't have to be there, but if it is, it can be there one or more times. A sum expression is a multiply expression, a mul expression with a sum operator and a mul expression. Again, it could just be this, but there could also be one or more sum operators followed by other mul expressions. So, and a sum operator is a plus or a minus. A mul expression is a unary expression followed by a multiply operator and another unary expression. Again, we don't need this part, but it can be there. And if it is there, it can be more than once. A multiply operator is a times, a divide, a mod, a left shift, or a right shift. The unary expression is unary op plus a size expression. And a unary op is either plus, minus, this is just to make negative numbers, for example, or a bitwise complement that will flip all the bits in the expression and the value. And a size expression is a size operator followed by a terminal expression. A size operator is either a left parenthesis, a right parenthesis, or an @ sign. The left parenthesis, typically these expressions will be 2-byte values. Everything will be calculated as if all of these values are 2-byte values. The left, the less than sign here, what that will do was it will make it a 1-byte value, and the value of that 1-byte value will be whatever the previous 2-byte, the low byte of whatever the previous 2-byte value was. And the greater than operator will again take that 2-byte value, make it a 1-byte value, but the value of that 1-byte value will be whatever the high byte of the previous 2-byte value was. And what the @ sign does is it takes a value which is maybe only 1 byte and forces it to be a 2-byte value. Okay? And the reason that I have chosen to use the @ symbol for this is because it reminds me of address. And kind of the idea here is that if you want to make sure that something is an address, because addresses are always 2 bytes long on the 6502, then you put the @ sign in front of it to say this is supposed to be an address, therefore it's 2 bytes. All right, the terminal expressions are the things that all of these things apply to, and that you could see it's a number or a name or a forward reference to a temporary label, a backward reference to a temporary label, or it could also be another whole sub-expression with parentheses around it. All right, and this grammar tells us that these things down here, the lower you are in this grammar here, the higher the precedence of the operators and the more tightly they bind. So, for example, because the multiply operators here are below the plus and minus operators here, that means that this expression will be parsed the way you expect, with the multiply operators happening before the addition and subtraction operators. And also, the addition and subtraction operators will happen before the bitwise AND, bitwise OR, bitwise exclusive OR operators, for example. All right? And kind of the tightest binding operator is here the size operators, because, and the reason for that is because you want to be able to do some sort of calculation, some sort of expression which calculate something and then say, hey, I want that to be a certain size, the result of all that calculation to be a certain size. Although now what I'm thinking about it, I'm thinking maybe we don't want these to be here because yeah, maybe. Yeah, maybe that's right. That is right. Let me just type something in here real quick. These being here means that if I do something like in my code, I have an expression like, let's say, 5 minus 2, okay? And if I want to now take the bitwise complement of this, if I were to do this, that would not be what I want. This will be the bitwise complement of 5. This will bind tighter than the subtraction. This would be the bitwise complement of 5 minus 2. If I want to have, I have to do it like that to say 5 minus 2, which is 3, and then take the bitwise complement of 3, right? And I think that's about right, because in the same way, when I have these things here, if I say 5 minus 2, but now I want that to be a 1 byte value, I do like this, right? Because this normally would bind tighter than the addition or subtraction, so I need to have the parentheses around it, and the same for this right here. That all looks good to me. I want it to be necessary to put parentheses around these other things in order to do this, because otherwise this would be 5 treated as a 1 byte value times 2 treated as a 2 byte value, which would then turn it back into a 2 byte value. A 1 byte value times a 2 byte value is going to give you a 2 byte result. So it's better that you have to do this, which is what we do if this binds tighter. And really, let's see, what about plus or minus? Well, the order of these things may not matter so much, whether or not this is higher precedence than this. They're both a type of unary operator that comes to the left of whatever it is. So this would mean take the bitwise complement of 5 and then make that a 1 byte value. And because these things are only, because these things are just unary operators, the order actually matters a lot. So perhaps these can all go into one level. Like that. All right, and then this here would be term exp. So see, here I am just changing on the fly. Didn't plan everything out in advance, changing stuff on the fly. And I think this is fine, because even if there were different precedences, it's the order that would matter. Yeah, so I think we'll do it like this. And we'll later see if this causes any problems in practice. If it does, we can go back and rearrange this. So here's the grammar. And we can basically use this grammar directly to write the code. And that's how the method of recursive descent works when you're parsing expressions. I have a routine called expr. I'll have a routine, it will just jump to a routine called orexp, right? And I can do that here. All right, I'll say JSR orexp. All right. And now orexp, not op, orexp is going to call the and exp routine, and it's going to look and see if there's an or operator. And if there is, it will try to call AND-X again, right? So this will JSR AND-Exp. And then after doing that, there will be a value here in this expr type expr val. And then it will scan. And it will see if it gets one of these two types of operators. All right, if it does get that, it'll go down somewhere. Otherwise, it'll look for, if it didn't get that one, it'll look for this one. And if it finds that one, it'll go down there. Otherwise, it didn't get any of either of these possibilities, so I'll unscan it. Okay. It will unscan it, and it will simply return as its value whatever it got here. Okay. So it called AND-X to parse whatever is coming. It then, after that came back, it said, okay, I'm going to scan and see if I get a regular OR, bitwise OR. If I don't, I'll look and see if I get bitwise exclusive OR. If I don't, then I'll unscan whatever I just got here, and I'll return the value of this as my value. All right, and to know exactly how to do that, I need to think more about these things here. So OR exp1. What this does is when we get and we called AND-X that gave us some value, and then we get a bitwise OR operator, we need to call AND-Exp again to get another value, and then we're going to bitwise OR the value from this one and the bitwise and the value from this one together. But we cannot put both of those values in the same thing here. That doesn't work, right? So what we're going to actually have to do is first off move one of these things. So this expr type and expr val is the result returned from parsing an expression to other parts of the code. So what we need to do is we need to have some other little variables here. And let me think. This could end up changing. This could end up being something which doesn't work. But for the moment, I'm going to do it like this. So when I call and get this AND expression here, let's go ahead and copy this. We're going to say this thing returns its value in these here, right here, expr type, expr val. Let's just copy these. Actually, I think I'll do it this way. It's not any faster or better, but it just maybe looks nicer. X1 type, X1 val, store y, X1 val plus 1, and this should be a 1 here. Okay, so I've taken the result of an expression and copied it into the expression 1 variables. Then I go to scan this stuff. If it's not there, if I don't get these operators, I unscan it and I can just return, because the result of this thing is still an X per type and X per val. Okay, if I did get it, I'm now going to JSR and X again. And now what matters is what this was. And at this point, I know it's in a bitwise OR expression. And there is a concern about the type because, for example, one of the things I'm trying to OR could be an absolute number of some sort, and another could be a label. All right, my expression could look something like this. Or how about I just like this? So, or my lab as a label. So what I'm doing here, this is an address, and I'm going to set a bit in that address for some reason. I don't know why. And this type here is going to be the type, it's going to be type relative. It's an address. You can, if you relocate the code, this thing can be moved around. But now that I'm setting this bit, is the result of that something that can be relocated or moved or not? And that is a very good question. A question that actually it's almost impossible to answer because I don't know for sure what the purpose of this is. Why is the programmer trying to do this? Is he trying to create something which is an address or not? But I think probably it will end up having to be not relocatable. But we don't have to worry about that for right now because I'm not really worrying about those types at the moment. For the moment, we have only the types 0 meaning undefined and 1 meaning defined. So for the moment, I don't have to worry about that. I'm just going to go ahead and load the value of this thing here and bitwise OR in that thing, and then put it back into X per val. And then okay, so what I've done is I've gotten a partial expression, an AND expression. I've gotten a bitwise OR. I've gotten then another expression, and I've just bitwise OR'd them together and put the result here in X per val. Once I've done that, I'm welcome to go back up here to this point right here. So I'll call this OR X0. And actually, that's not right. I need to take this X per val. Maybe I should not put this in X per val. I should put this in X1 val. Okay, and the reason is because I've done that here. So basically, the situation is I have an expression on the left, then the OR operator, and an expression on the right. I'm putting the expression on the left in this X1 variable here, X1 type, X1 val. And then I'm getting my thing, and now I'm getting the right-hand side, and the right-hand side, I'm putting, the right-hand side comes back in X per val, but I'm putting the result of bitwise ORing those two together in the X1 val. The reason being is that now I can go back and get another I can get another. That's what this plus here means. I can get another and another and another OR operation or operator. And the left-hand side, this is now the left-hand side, like blah or blah is now the left-hand side for any future OR operators, so it should be here in x1 val. All right, and at this point, then, I can jump to or exp 0. But that means that at this point, if I do not get a operator, I actually have to copy this thing from x1 val back into expr val. Actually, this is your type. Plus 1. Okay. So I get the left-hand side, and x returns its value in expr type, expr val plus 1. I move that to x1, type and val. Then I look for a bitwise OR operator or bitwise exclusive operator. If we assume I don't get one, then what I'm going to do is unscan that thing and then just copy this thing right back into expr type and expr val and return. If I do get one of these operators, then I'll go down here, I will call andexp again. And when I do that, I will take whatever is an expr val, which is what andexp returned, and I will bitwise OR that with what is an x1 val. So this is the right-hand side of the OR operator. This is the left-hand side of the OR operator. And store that in x1 val. Store the result of that bitwise OR in x1 val, because this will be the left-hand side of any future bitwise OR operators. And then I can jump right back up here and look for another one. If it's not found, I end up copying x1 back to x1 type and x1 val, get copied back to expr type and expr val. Okay, and I haven't done anything with the type yet, and I should do something with the type, which is the thing I should do with the type right now is I have to recognize, in the moment, I only have defined and undefined as types. By the way, I probably won't need this number 2. All right, is I have defined and undefined types. So what if I have two labels, one of which is defined, like this, the other which is undefined, okay, because I'm going to have my, I'm going to do result is foo plus bar, and bar is down here. It's a label for some code. All right, it's a label for some code here. So at the point when I come through in the first pass, I say foo is 3, that's nice. Bar is undefined. So I have a defined symbol and an undefined symbol. If I add those together, what do I get? Well, an undefined symbol has a default value of 0. So the result of the value is going to be 3 plus 0 is 3. But I need to say that this is type undefined, because if bar is undefined, result cannot be defined. All right? And like I said, as of right now, I have only the types defined and undefined. If I have two defined things, there'll be one, the type will be 1 and 1, that's defined and defined. If I have, and that the result of 1 and 1 needs to be 1, defined. If I have 1, 0, or 0, 1, that means one of these is defined, the other is not. The result needs to be undefined, that is a 0. If they're both 0, they're both undefined, the result needs to be undefined. So it's just an and of the type. The type has to be anded. Okay, so here's where I perform my bitwise OR. So I'm going to load actually, let me just do it here. It doesn't matter that much, but I'll do it up here. So load X per type. Bitwise AND X1 type. Store that in X1 type. Later, when I have all the different types, this type, finding the result of the type of some operation will be fairly complicated. But at the moment, it will always be this bitwise AND. Okay. So that's all nice. Now I need to take care of the bitwise exclusive OR. And the easy and pretty way to do it, although not necessarily the most efficient way to do it, is just to duplicate all this code here. All of this code here. Okay, but instead of doing ORA here, I just do EOR, exclusive OR. All right, and then jump back up to OR X0. All right, so here is the code I need to handle the OR expression. This routine will call AND expression to get all of this stuff down here. If there's an OR operator, it will consume it and call AND expression again to get the right-hand side of the expression. And then it will actually bitwise OR here, or bitwise exclusive OR here, depending on the operator, the two values, and just basically keep getting OR operators until there are no more, and then return the result. Okay? Now, there is an issue here, a problem. There are two problems with this code here so far. First off, it is possible that the AND expr subroutine right here has an error and returns some sort of error. So there and here. We'll have to check for that. At the moment, I don't really know what kind of error there could be. Oh, actually, three problems. This thing here, no. If it is looking for a bitwise operator and doesn't get it, it'll just unscan it. So it doesn't have to worry about that here. That's not going to be an error that's generated here. Okay. Right. And then the other issue is that since this is a recursive thing, this X1 val really, these variables really should be something that won't get wiped out. Like if the AND expr routine here uses the X1 type and X1 val variables, then notice I've called AND and I put my result of this here, but then I call AND again, and if it uses the same variable, it will destroy their values so that at this point they won't be available to me. So that's the kind of thing that maybe should be stored somewhere else, right? This is the recursive nature of the thing and why the stack matters, and I might have to worry about that. I could have a separate, instead of X1 type and X1 values, could be OR type and OR val, and then AND could have AND type and AND val. That would solve the issue of the expressions, these routines down here, destroying my value that this routine needs to use. But it doesn't solve the problem that I could have something like this, an expression that looks like this, like 3 or, and then 5 or 7, or 6, something like this. In this case, right, this one is going to actually be evaluated first. Well, actually, I'm sorry, that's not true. It'll first look at the 3. It'll store this 3 in x1 val. It'll then go here and say, aha, I have a new thing. So it'll evaluate 5 and store 5 in x1 val. And then it will get 6 and OR that with 5 and put that result in x1 val. And then return it in x per val, but then it will be blown away. So this is a problem. So we need to find a way to do this. And yeah, there's going to have to be a stack of some sort. But we probably don't want to use the 6502 stack for that, although maybe we could. It's not that much space that's required. Yeah, it's not that much space. So if we use the 6502 stack, how would that look? Probably we would need to store both of these things on the stack. So that would be 4 bytes. Now 4 bytes is not exactly a deal breaker. I'm just thinking about it. I'm not really, the thing is, I'm not 100% sure we need to store both of them on the stack, but we do have to think about this. This is the real problematic case, the one I just showed, where we have, something like this. This kind of expression is the one we really have to worry about. Because this will store something in one of the things. Yeah. My mind doesn't feel sharp right now, but I'm thinking that we notice here we're really keeping our information in the x1 variable, right? We move the result of this to x1 variable. When we get another operator, we just, the x per type variable is only used to retrieve whatever this gives back to us, and then we put the results of our operation in the x1 variable. And then when we are ready to leave, we take x1 variable and put it back in x per type. So I think it's safe to only save this x1 variable on the stack. Okay, and we would have to do that right here for x1. Push it, push it, push it. Okay, then jump make our recursive call. Okay, and here, retrieve it. Okay, of course, this was actually all wrong. It's not supposed to be this, it's supposed to be this one. Okay, and we would have to do that down here as well. But actually, instead of storing it here, we could just push it. So push that, push that, push that. And actually, I would prefer to do them in exactly the opposite order, because I always like to push the high byte first. Well, the type, whether the type or value comes first doesn't matter. So we'll load the expert type, push, push, push. That goes away. If we don't get anything, then instead of loading from here, we'll just pull it. Okay. So that. Okay, so we didn't get an operator, so we'll just pull what we just stuck on the stack and pull it off. Pull out what we just put on the stack and put it back in expert val variable. Okay, that looks nice. If we do get a bitwise operator, now we don't have to push it here. Okay. Okay, we've put off expert val, we've put the val. So how do we push it up? We push the type first, then the value high byte, low byte. And now we're pulling the value low byte, high byte, then the type. So we can jump to and expr. And it's going to return its result in expr type and expr val. So now what we can do is we can get rid of that. We can actually just pull, this is going to be the low byte of the value. And then aura expr val. And then we have to have some place to store it for a second. The high byte, or with expr val +1. And have some place to store that for a second. And then pull the type. And end that with expert type. Okay, and once we can push that right back up on there. And we can actually just store this in, we can put this in X, that would be fine. Put it into X. Put that into Y. Okay. And then we can TYA, push it, TXA, push it, and then jump to OREXP 0. All right. Now I'm going to just get rid of all this stuff here. Don't delete. Bring it back. All right, and now we're replacing these with exclusive OR. Otherwise, the code is the same. Okay, and now what we've done is instead of using this variable called x1 type and x1 val, these variables, I should say, we're just putting it on the stack. So that means our recursive call requires 5 bytes on the stack. It requires 2 bytes for the return address. It requires 3 bytes, 1 byte for the type and 2 bytes for the expression value. So 5 bytes in the stack for a recursive call. If the recursive and when we call here, we're going to go all the way down to terms. So OREXP is going to call ANDX, which is going to call SUMX, which is going to call MOLX, which is called UNARYX, which is going to call TERMX. So 1, 2, 3, 4, 5. That's at least 5 levels of stuff stored in the stack. 5 times 5 is 25. And then, of course, a term can go back up to OREXP. So if you have, it depends on how much your parentheses are nested. If you have like 3 levels of nesting, that will be 15, or 1, 2, 3, 4, 5. Oh, OREXP. 15, maybe 5 plus 15 plus 1, or actually maybe, yeah, 18, 20 times 5 bytes. It could get expensive. It might blow out our stack. It might blow out the stack. But what I'm going to do is I'm going to leave it like this just very temporarily, or at least for now, because I want to make sure that it works. And if it does work, then I'll probably come back and have a separate stack somewhere to take care of these expressions so that I don't blow out the 6502's own very limited hardware stack. But how this thing looks about right to me. All right. And what I haven't done yet is I haven't handled the situation where there's some sort of error, syntax error. But what that will actually be is when we get down here and we get something which is not a left parenthesis, not a number, not a name, not a forward reference to a temporary variable, not a backward reference to a temporal variable, that's when there's going to be an error. And that will have to then be propagated all the way back down through these things. So this is only one of the routines of the expression parser, but this is basically how it's going to work. And I think now is the time to stop, and next time we'll get back in and do a little bit of extra work here. In fact, I might just go ahead and write some of the code, try to see that I can actually parse expressions and get a value out, and then go back and make sure that I don't blow out the hardware stack. So until next time.